So, in part two, we're going to pick up where we left off. Where we left off was with the type of bonds that have to form in order for us to get a mineral in the first place. Just as a quick review, they were covalent bonds and ionic bonds, where electrons are shared or exchanged. Covalent are considered stronger. Ionic bonds are pretty weak. Metallic bonds are kind of interesting because that's what allows metal to be so malleable. You can hit it with a hammer, and basically what you're doing is, as you squish the atoms down, the electrons kind of can still move around and hold the things together. The van der Waals bonds, which is where we left off, are the weak bonds called intermolecular force that hold, in this case, these sheets together. So the orange lines represent the van der Waals bonds holding the more strongly bonded sheets together. And in this case, these sheets are held together probably by covalent bonds. So the van der Waals bonds are there. Because they're weak, that means that those sheets can move past each other. Although the sheets stay intact, there's essentially a plane of weakness. So, how do we go about identifying a mineral? Well, the mineral's identity is going to be based on its chemical composition and crystalline structure. If we want to, we can take a mineral sample down to the lab and go through kind of in some cases, a pretty intense process to determine its chemical composition. The crystalline structure, there are special pieces of equipment that we can use to determine the crystalline structure of a mineral. We do not have one of those in the lab, and we are not going to be determining chemical composition. But this is what the mineralogists use when they determine the identity of a mineral. So we're just going to stick with that for a few minutes and talk about where it takes us. First of all, we have to, if we go back to this, you'll notice it's chemical composition and crystalline structure. Here's an example of two minerals with exactly the same chemical composition. In this case, it's pure carbon. However, they have different crystalline structures and different types of bonds. So in the case of a diamond, the framework is very strongly bonded carbon atoms with covalent bonds connecting all the carbon atoms. In graphite, there are some covalent bonds in the sheets, but the sheets of graphite are connected to each other with that intermolecular force, those van der Waals bonds. So it's a much weaker bond. And I don't think you would mistake diamond for graphite. They have very different physical properties, which we will talk about in a little bit, and even more down in the lab. But this is an example of why the crystalline structure is so important, because both of these have the same composition, but the different crystalline structure gives them some very different characteristics. The other thing that we want to talk about when we talk about crystalline structure comes to a whole group of minerals that we call the silicate minerals. And so I want to spend a few minutes talking about the silicate minerals. The reason the silicate minerals are so important is because silicon and oxygen are the two most abundant elements in the Earth's crust, which means that most of the rocks and minerals that we find will be made of silicate minerals. Not all, but most. And so we want to look a little bit more closely at this very, very common group of minerals. And we'll be referring back to minerals in this group off and on throughout the semester. So at the core of the silicate minerals are what we refer to as the silicon-oxygen tetrahedron, or the silicate tetrahedron. You'll notice there's one silicon atom in the middle, and it is bonded covalently with 4 oxygen atoms. So the oxygen atoms kind of surround the silicon atom. And the oxygen atoms need to keep as far apart from each other as possible. And so they set up this little pyramid that we call a tetrahedron. The base of the pyramid is a triangle, and each of the sides of the pyramid are a triangle. So it is a four-sided object, a pyramid with a triangular base and three triangular sides. So that's what the tetrahedron is. The cool thing about this is the oxygens are only sharing one electron with the silicon. And that means they each have still a free slot in their outer shell, which they can then use to bond with other things. So this means that the little tetrahedron we have here has a lot of possibilities for creating structures, crystalline structures. So let's look at a few. This slide shows you how they can bond with each other. So a lot of the silicate structures we look at their core have these little tetrahedron bonded together. You'll notice these two tetrahedron are just sharing one point, and that allows that shared oxygen to occupy both of its open spots in the outer electron shell. So that's why they're able to do that. But you'll notice that even this pair, all those oxygens sticking out there, still waiting for something to bond with. So when we build a silicate mineral, one of the things that can happen is you have these individual tetrahedra, and they bond to other elements. So the space in between the tetrahedra is going to be occupied typically by metallic elements. So you might find iron and magnesium in there. You might find calcium. You might find potassium. There are a whole variety, really an alphabet soup of elements that you can find occupying the spaces in between the tetrahedra. So this is kind of the simplest structure where you still maintain those individual pyramids and then bond them together with other elements. Olivine is a mineral that's an example of this kind of structure. If you hook the corners of the pyramids together, you can put them into a chain. And you can make a single chain. You can make a double chain. So you can see two chains are linked together. And then within this structure, between the chains, what holds the chains to each other, in case of the double chain or the single chain, is going to be other elements. So when we look at, in the lab, we'll be able to look at the chemical formulas for some of these silicate elements. And what you'll see is there can be some pretty complicated chemical formulas there, where you bring in all the other elements that are holding these chains together. If we can have a double chain, we can have a sheet. And the final one that I'm going to show you is a complicated three-dimensional structure. And a couple of examples of elements of minerals with this are quartz and feldspar. And it turns out that quartz and feldspars are our two most common minerals in the Earth's crust. So, and within this three-dimensional framework, there will be incorporated other elements, with the exception of quartz. So quartz has a chemical formula of silicon dioxide, or SiO2. So it's only silicon and oxygen. But the feldspars are actually a group, and they incorporate a bunch of other elements in them, including potassium and calcium and sodium. So you can get a lot of other elements into one of these structures as you build a mineral. So we've got all these minerals. In fact, well over 2,000 minerals have been identified. How do you tell them apart? We already said that we're not going to be going down to the lab and figuring out the crystalline structure and chemical composition. So what we're going to do instead is we'll use the physical properties. It turns out that because of the variation in crystalline structure And because of the variation in chemical composition, each mineral has its own unique set of physical properties. And so if we go back to our example of diamonds and graphite, nobody would mistake diamond for graphite. Graphite is the silvery gray mineral that we use in your pencil. It is very soft. It's so soft you can scratch it off on a piece of paper, whereas a diamond would cut right through that paper. Diamonds are clear. Graphite is opaque. Diamonds are clear and kind of white if they have a color at all. Graphite is definitely a silvery color. Diamonds have a sort of a glassy shine to them, where graphite looks more like metal. So these two very different minerals have the same chemical composition, but that different crystalline structure results in some very different crystalline or physical properties. And so the key properties that we're going to look at down in the lab are going to be color, pretty easy to identify. Cleavage, which is the tendency of a mineral to break along planes of weakness. And as you might imagine, that's going to relate to the types of bonds that are present between the atoms. Hardness is the resistance to abrasion. So diamond, for example, has a hardness of 10. And again, all those covalent bonds holding it together is what gives it such a high hardness. Whereas graphite has a hardness of 1 because it's held together with those very weak bonds. Some other properties are the streak, which is the color of a mineral in its powdered form. We have little porcelain plates. You drag the mineral across it and look at the color of the mark. Luster is how the light shines off of the mineral. And we're going to break that into two really broad groups, metallic and non-metallic. But within the non-metallic area, you have everything from dull, which is not shiny at all, to glassy, which can be pretty shiny, and to things like silky, which is somewhere in between. So there are a lot of different descriptors for luster. Some other mineral properties that we might notice and use are the crystal form. That's a little bit more difficult for us down in the lab because most of our mineral samples that we look at will not show their true crystalline form. The mineral has to have room to grow in order for that crystal form to be visible and expressed. And so there are only a few samples where we can actually see that crystal form. Density can be an important characteristic. Some minerals are very dense and they feel really heavy in your hand. A few of the minerals we have are magnetic, so magnetism is an important property. And a couple of our minerals will react very strongly when you put acid on them, and we will use that as a diagnostic property for those minerals in the lab. So that's some stuff to look forward to in the lab if you haven't been yet. And so that brings us to the last slide of this group, and that is just the lab is going to be mineral identification. We're going to identify the physical properties, and then we're going to compare those properties to a chart in the lab book to determine the identity of each mineral. And so that's it for this week's slide presentation.